I'm very pleased to introduce you, Steve Hesselbo. In fact, I met Steve in a meeting, in a workshop, fantastic workshop that was organized by Paul Olsen in Utah. It's 2 years ago. And we met there and I learned about the JET project, and I found it really interesting. And I was very lucky that Steve also joined my proposal for an ERC, the AstroGeo project, which aims to use the geological record to be able to constrain the astronomical solution. And so we had last month, we had the first talk by Felix Gradstein about the new GTS 2020. And I'm very pleased that Steve could, the timing was perfect because they are drilling just this month or the previous month, it just finished. And so Steve, you will be able to give us very fresh news from the coring you made in England. So Steve, it's your turn and we will be all waiting for your talk.
Thank you very much, Jacques, and thank you everybody for attending. I want to divide this talk into three parts, really. One is an introduction to the JET project as a whole, and then I'm going to talk a little bit about what the JET group have got scientifically from working on legacy cores, in particular the old Mokris core. And then the last third will be a kind of update as to how we've got on at the new borehole site, which is a place called Prees in the UK. So before I start, I just need to move the window from Zoom out of my way. That's better. Good, right. So the JET project has now quite a long history, and it's a bit like a snowball. It seems to be growing and growing with time. As well as myself as PI, I have a number of other co-Is, and the original cast of co-Is were Christian Bjerrum in Denmark, Linda Hinoff, and Ken Miller in the US, Jim Ryding in the UK, Bas van der Schutbrugge was in Germany at that time, and Thomas Vonneck also in Germany. And what's in the name JET? Well, JET stands for Early Jurassic Earth System and Timescale, but most of you will know that JET is also a kind of semi-precious material that's been used since Roman times, that forms from early Jurassic trees in particular at an interval in the Taurasian in the early Jurassic, known as the Taurasian oceanic anoxic event. So it was quite good in terms of symbolism of the major environmental changes that have taken place at this point in Earth history. Here's some images, the classic jet rock locality on the Yorkshire coast. Some pieces of jet that got far and wide in Europe from these locations, and an image of tree rings indicating actually strange seasonality that was taking place during the early Jurassic, during the Taurasian oceanic anoxic event. Okay, so now I need to advance. For some reason, the slide has stopped advancing. Maybe we'll try here. Here we go. So the JET project was proposed really in line with a lot of work that's been going on, supported by scientific drilling through the decades, taking as its kind of key efforts through IODP over literally decades, taking long continuous sedimentary cores in the oceans as an archive of Earth history. And this has come to fruition, particularly for the Cenozoic and Cretaceous recently. For the Jurassic, it's not so much IODP that is relevant, because clearly Jurassic oceanic sediments are relatively rare. So in our case, we set up a project and made a proposal to ICDP, the International Continental Scientific Drilling Project. And ICDP funds workshops to develop project ideas. So if anyone in the audience is interested in going down this line, one thing that you really need is persistence. And Ken Miller warned me this at the beginning of the project. Here's Ken at a workshop that we first held in 2013. So the project idea came about in 2009. We had ICDP approving funding for coring 5 or 6 years later. The Natural Environment Research Council approved funding a year after that. And then it took us 3 years to work through some of the difficulties we had in getting a site organized and coring underway. We were about to start in March 2020, and then the pandemic came along, and then that left us with drilling operations during November and December this year. So something like 11 years after the original idea for the project came about. Some of the people in the photograph here have already introduced themselves, like Wei Mu, you can see in the front here, and I know that Misha is also in the audience for this seminar, and there may be some other people there as well. So what is JET trying to achieve? Early Jurassic Earth system and timescale. So the timescale is really quite an important aspect of this. And if we look at various compilations of geochemical data, and here's an example from a recent paper that we published in Earth Science Reviews from the early Jurassic. So this is Hettangen and the lower part of the Sinemurian, where we take fossils and we look at geochemical proxies for environmental change in those fossils. We try to plot them up against time, and you've obviously got the oldest on the left and the youngest on the right in this diagram, and things like oxygen isotopes going from relatively cool paleotemperatures, which is what the oxygen isotopes partly indicate here, going to relatively warm, or carbon isotopes here. Again, these are all from fossil shells of various kinds in different localities. We can see spikes and then long-term trends and so on. But the timescale here, through necessity, is just based on assuming ammonite subzones are of equal duration. And we know that for all sorts of reasons to be wrong. But the early Jurassic, for a long while, has been one of those parts of the geological timescale where getting a very good age model for the biostratigraphic subdivisions has been really problematic. So in this case, this is the aftermath of late Triassic mass extinction, which occurs around about here. And the timescale is important because we want to know what the rates of change are in these gradients you see in these graphs are quite spurious otherwise in terms of understanding rates of change in the context of major environmental perturbations. So there's the late Triassic mass extinction, and then that's the time scale, which is poor. And here's another example a bit later in the early Jurassic. This is the Taurasian oceanic anoxic event. Again, these are data from various localities showing changes in paleotemperature, probably from cool to very warm to very cool. And these apparently abrupt changes may be more or less abrupt, but again, we've got here a timescale that's just based on subzones. So JET was kind of set up both to improve our understanding of the paleoenvironmental changes that were taking place through the geochemical chemostratigraphic work, but also to put that in the context of a proper numerical timescale as best as we could manage it. So Northern and Western Europe is particularly important for the early Jurassic. It's important historically because people have been working on the Jurassic outcrops for a long period of time, and many of these lower Jurassic stages, the Hettangian, Cinnamerian, Pliensbachian, Taurasian, are defined in Northern and Western European locations. There are two in the UK, the base Pliensbachian and base Cinnamerian. Here's the golden spike for the base Taurasian, which was put in a couple of years ago from Portugal, and the base Hettangian, which is the same as base Jurassic, is an Austrian location. So in order to define the early Jurassic timescale better, Northern and Western European locations are probably the best ones to focus on to begin with. Incidentally, the golden spike, I went to two events for inauguration of these of GSSPs, and the golden spike from one was stolen about an hour after it was put in place, because it was believed that it really was a golden spike rather than a brass spike. I understand it was returned sometime quite soon afterwards. So why don't we just work on the outcrops then, if they're that good? And here are a couple of examples from the Dorset coast, the so-called Jurassic coast in southern England. And these are very well explored. They've been explored using a number of stratigraphic techniques, including cyclostratigraphy, including biostratigraphy, including chemostratigraphy. These two actually quite good examples that show potential astronomical cycles in the outcrop. The problem is with the outcrops is they're relatively thin, and that the facies that are represented are diverse, shallow water facies in which we suspect there are many gaps and breaks in sedimentation or changes in sedimentation rate. So from that point of view, they are non-ideal. But as I say, there's been a long history. Here's one of the first scientific reconstructions of paleoenvironment. This one, Delabesh's reconstruction of a more ancient Dorset, showing some of the supposed ecological relationships between the organisms in these marine rocks that characterize much of Northern and Western Europe. And those marine fossils are very important archives for geochemistry, very important archives for chemical conditions in the early Jurassic oceans at times of these environmental perturbations. So clearly, astrochronology is very important now in developing the geological timescale and understanding rates and processes. And if we look at this compilation from Chengju Wang, for example, from 2018, we can see in summary here, now the time is going from right to left, this case. This is the Triassic-Jurassic boundary, here tangent Cinemurian planes back into Taurasian. Set against here the long eccentricity metronome, that cyclostratigraphic or astronomical, astrochronological studies are few and far between for this interval, and the Cinemurian in particular stands out as an interval that is very poorly explored in terms of cyclostratigraphy. So number 8 here, this is a study from Ikeda et al. From Japanese oceanic ribbon cherts and shales, which is a beautiful succession and analysis is in its own right, but those are very poorly constrained biostratigraphically and in terms of any other time constraints. So, so this is a major gap in our understanding of cyclostratigraphy, connecting the more ancient pre-Jurassic past, which is in many cases very well explored, for example, through the Newark Basin, Colorado Plateau sequences, and the more recent geological past, which is represented by oceanic sediments. The location of the particular borehole sites that I want to talk about in this talk of Mokris and our new Pries site is here in its paleogeographic context. So it's a mid-latitude setting in the middle of the seaway that connected the Tethys Ocean at the time, went across Pangaea, connecting through to the Arctic region. And with these connections, both to the north through this Viking corridor and then eventually through the Hispanic corridor to Panthalassa as well, the biostratigraphy of this region is pretty cosmopolitan in the early Jurassic. So in terms of defining stratigraphy based on faunal contents and floral contents of the rocks, this is a very useful location to define those parameters. And it's also close to these global reference sections or golden spikes as well, which are the defining points for the boundaries. So the original plan for JET was to re-drill this important borehole that was drilled originally in 1967-1969 at a location called Llanbedra in West Wales. The more specific name is Mokris Farm, and that's been shortened over the years to Mokris, so people tend to refer to this borehole as the Mokris borehole. And that location, this map is a little bit complicated. It's a geological map that shows both the onshore and offshore around the British Isles. So blue in this main map is Jurassic and early Cretaceous. You can see the various faults are shown here and the different basins. So down here is the Wessex Channel Basin of Dorset, Bristol Channel Basin, which has got the Basin Miriam GSSP. Down here, this is Wales, Mokris, right on the coast of Wales, on the edge of something called the Cardigan Bay Basin. And then the base Plinsbachian GSSP up here in Robin Hood's Bay in Yorkshire. So Mokris was a remarkably thick early Jurassic succession. In fact, it wasn't even when it was drilled, they weren't expecting early Jurassic at all, of a remarkably uniform mudstone lithology. And it yielded a lot of ammonites, and so was amenable to dating by biostratigraphic means. So that was our primary focus, and there were good reasons that I'll explain in a second to re-drill Mokris. In the end, it turned out to be impossible in terms of budget, also pretty much impossible in terms of the sensitivity of the site. You can see here it's in the very kind of highest level of conservation area in a European classification. So it was okay to drill in 1967 to 69, but much more difficult logistically to re-drill today. And so eventually, for reasons I will explain, we switched to drill instead at this location, an underexplored and very poorly explored basin, Cheshire Basin, here on the Welsh-English English border at the location called Prees. So firstly then, Mocrus, what, as a legacy resource, why is Mocrus so important? So you can see here from this sort of thumbnail sketch of the succession, with the shallowest at the top, deepest at the bottom, we have something like 1,300 meters of mudstone representing all of the lower Jurassic stages: Hittangian, Cinemurian, Pliensbachian, and Taurasian. And all the ammonite biozones were recovered and recorded in the original borehole. It was also recently zoned in terms of forams, and there's been some work on nanofossils as well that's shown it's possible to get a detailed nanofossil zonation from the same borehole. And so the advantage of this is that instead of putting together a record that is a composite from many different locations where there's correlation error between those locations, we can get really quite highly refined biostratigraphy from a single location. There were some geophysical logs, but they didn't go right to the bottom of the hole. I think there must have been some difficulty with the stability of the bottom of the hole. It was, after all, the hole was drilled over a period of more than 2 years. And the original recovery was something like 97.6%, represented by this red bar here, including good recovery at the bottom of the hole. However, when we go to the archive today, only 59% of the borehole is still there as core slabs at any rate, because the bottom part of the borehole, the core, was broken up. It's not entirely clear why this was. It may have been a narrower diameter anyway, so there was less material. And it was certainly broken up for its paleontological content. The remaining fragments were put into bags that were averaged over 1.5 meters. So there's a collection of those bags in Rutgers core store, strangely. How they ended up there, I don't know, but also at the BGS in Keyworth, there are these bags. So I say their interval averaged over 1.5 meters. And it'll become apparent shortly why that 1.5 meter averaging is rather an unfortunate averaging to have decided on. Nevertheless, particularly for the upper part of the old Mocrus core, it's excellent as an integrated biostratigraphy, cyclostratigraphy, chemostratigraphy, and magnetostratigraphy. All of those have been proven to work. It's very good for paleoenvironmental proxy records, so geochemical and non-geochemical proxies for environmental change. And we think we can correlate at least a few levels to some precise uranium lead ash dates from the Western Americas in order to try to constrain with radioisotopic ages some of the cyclostratigraphy from this location. So what I want to do now is just give you a flavor of some of the work that's been completed on Mocrus. It's by no means all the work from Mocrus, and I know that there is a lot that is in the pipeline at the moment as well. And I think there are a lot of papers that are going to come out on Mocrus over the next 2 or 3 years that will build on some of this initial work. Here are some of the core photographs from the upper part of the Mocrus borehole, and here's the Pliensbachian, for example, on this right. These 4 core sections from the Pliensbachian and 4 core sections from the Taurasian. So you can see here these are actually pretty good state the core slabs there. And you can also see that there are dark, pale, dark, pale, dark, pale cycles. And these are in boxes that are about 1 meter in length. So these are, we interpret the precession cycles that go all the way through the Pliensbachian, and we think also pretty much all the way through the Taurasian as well. Unfortunately, you can see from this, each precession cycle is about 1.5 meters thick. So that means that this averaging of material that was broken up from the lower part of the core has basically wiped out any of the precession signal that could be extracted from the old Mokras core. And that was one of the major justifications for trying to re-drill, particularly the lower part, the Sinemurian and Hitangian part of the core, where there is least preservation in the archives at the present day. Here's a photograph of a younger looking Misha Rule making some measurements using handheld XRF, which was all we could do at the time, from core, to build up a time series of elemental abundance through as much of the Mokras core as we could do. I do notice I've managed to draw a red line somehow on all these slides, so I sort of apologize for that if it's distracting. It seems to be there on all of them. Never mind, you just have to filter it out in your minds if you can. So the work that Misha led with, some of it is kind of illustrated here, putting those individual precession cycles into their larger scale context. This was published in a paper in Earth and Planetary Science Letters in 2016. So we can look at rubidium content, for example, which is shown here with the black squares, iron, titanium, and in this case calcium content, with the core photographs laid underneath that calcium curve to show the pale dark alternations, which are essentially limestone shale alternations. The interpretation that we came up with at the time was that these were precession cycles, and that if one looked at long time series, they could be bundled into fairly clear 100,000, approximate 100,000 year short eccentricity cycles, and those short eccentricity cycles bundled into fairly clear 405,000 year long eccentricity cycles. And so this is a compilation for the whole of the Pliensbachian, representing all of the ammonite zones from the Sinemurian to the Taurasian, and interpreted in terms of long eccentricity cycles. So this is about 400 meters eccentricity cycle based interpretation set against, in this case, an existing global polarity timescale. So it's just taken from GTS 2016 or GTS 2012 at the time, and pasted on to, if you like, the Mokras record. Now we know from work that Wei-Mu Xu and Connell McNichol have done that we can actually get a very good paleomagnetic signal out of the Mokras core as well. So this will be elaborated in the not too distant future with paleomag directly from the same core. That gave us an estimated duration of about 8.7 million years for the Pliensbachian stage, which was what was used in GTS 2016 and 2020. So this was a starting point, and I think these are good hypotheses, but it's very clear that we now can hugely increase the amount of data that we have by multi-element core scanning using XRF core scanners. So instead of just limiting ourselves to a number of data, smaller number of data points for small number of elements, we can look at a much broader range of elements. And also work has been done, very detailed work on sedimentology and trace fossil occurrences, which also show cyclicity. So these cycles here, there's no doubt that they will be refined and updated, but hopefully the overall pattern will not change hugely. We can also see in this record here what seem to be long-term cycles in the carbonate. And whether those are under astronomical control or some other control is very much an open question. So that's the astronomical side of things from MOCRIS, if you like. There is also here an illustration of identification of non-astronomical impacts on the core. So we have here for the Taurasian, and this is work from Wei Mushu's PhD thesis, and also Lawrence Percival's PhD theses, where we can get things quite difficult to measure, proxies for example, weathering intensity, which is the osmium 187-188 ratio, relatively easy to measure proxies for volcanism, such as mercury, set it against carbon isotope record, which is very distinctive for this Taurasian oceanic anoxic event, and the paleomag from the same borehole. So all these data come from the same borehole, allowing us a very precise correlation to Karoo, Farrar, large igneous province, igneous rocks from Africa and from Antarctica, where there are some age constraints from argon-argon dating. So this allows us to relate the paleoenvironmental changes fairly readily and directly to non-orbital forcing, in this case large igneous province. And an area for further exploration in the future will be the interactions between the orbitally driven processes and those that are driven by by things like large igneous provinces. And then a last example from MOCRIS of the kind of work that is ongoing. Here's work from Jean-Francois Deconninck and a team who've been looking at mineralogy. So there's a big effort to characterize the actual mineralogy of the cores in terms of the environmental sensitivity. Here we've got examples of clay minerals through the whole Pliensbachian again, to take the Pliensbachian as an example. And again, we can see these long-term cycles in clay mineralogy, which are evidence of really quite substantial changes in paleoclimate through those intervals. Again, there's an open question whether those are under a tectonic or astronomical or some other kind of control, and work is ongoing at the moment to really focus in detail at these same kinds of analyses, but from smaller scale. At a smaller scale, those Milankovitch cycles that we've already seen from the original work that Misha Rule and others did. So lastly, from MOCRIS, I want to just put this one up. So this is now the whole MOCRIS record going from the Triassic Jurassic boundary to the end of the Taurasian. And these are organic carbon parameters. So pyrolysis analysis of organic matter, TOC, and carbon isotopes. And MOCRIS provides what is probably the longest, most complete carbon isotope record that we have for this time interval. Work of Wei Mushu and Marisa Storm to produce these. But this also shows the limitations of MOCRIS, because although we think we can recognize what are at least hypothetical long eccentricity cycles through the Sinemurian here in the carbon isotope record, we can never really get beyond that long eccentricity cyclicity with Mokras because of this interval averaging of the precession signal. So that's one of the reasons that we really have to go elsewhere, which brings me on to the PREES part of this talk and an update as to where we've got with PREES drilling. So where is PREES? Here's a geological map in detail of the Cheshire Basin, and this grey-brown colour in the middle is the early Jurassic outcrop. This is about 10 kilometres across from the northwest to the southeast. And there's a major fault here called the Wem Fault. So the whole thing is basically a half-graben structure. And there are a lot of seismic lines across this region from oil and gas exploration in the 1970s. Some of the earliest vibroseis came from this area. And we chose the PREES site because it was adjacent to a 1972 oil and gas exploration well, which was drilled to 3.5 kilometers. It was dry, there was no oil and gas found. The well was not cored, there were cuttings only, but nevertheless it gave us an insight into the likely Jurassic record in the Cheshire Basin. And here's a photograph of the old 1972 exploration well sitting here in this agricultural, rather easier to get permission to drill location. So what does PREES offer us in comparison to Mokras or to any of the other outcrops? Well, in these stick diagrams here, you can see here, this first one on the left is thickness with the stages color coded. So Hitangians purple, Cinemurian green, Pliensbachian red, Taurasian blue. And the series of boreholes here, you can see Mokras is by far the thickest and has the best representation of the lower Jurassic. By contrast, if we go to Yorkshire coast, Robin Hood's Bay, much thinner, although that has the GSSP. Similarly, the Somerset coast, Bristol Channel Basin, much thinner succession. That has the GSSP for the base of the Cinemurian, also cyclostratigraphic astrochronological studies. Sancerre, which is an important borehole from the Paris Basin, has a relatively expanded Taurasian, but poorly constrained and thinner Cinemurian and Pliensbachian. So PREES is sitting in here, and this was before we drilled. We thought that probably this was the record we would get, something like 600 meters representing Hitangian, an expanded Cinemurian of about 300 meters, and also some Pliensbachian at the top. So that then fills the gap between what we can get from Mokras, Taurasian and Pliensbachian, and what's reasonably well known from outcrop, which is across that Triassic-Jurassic boundary and into the Hitangian. So we're spanning that important gap at PREES. Here's the seismic context. This image was reprocessed by colleagues at the Institute for Applied Geophysics in Hanover, so Sonja Vardas and Thomas Vonik. About 15 kilometers across. It's a half-graben structure with the Triassic let down into that half-graben. And oddly, the Jurassic sitting in here in some kind of syncline, which might, well, this is speculation, might be something to do with salt withdrawal, because we know we've got salt in the late Triassic at the top here, and if the salt moves, it may produce this kind of synclinal structure above. But it's a little bit of a mystery as to what the substance mechanism is that's giving us a thick, complete, relatively deep water Jurassic succession at this location. If anyone has any insights into that, I'd be very happy to hear about them. So here's just a blow up of that with the well projected onto it and what we thought we would recover in terms of Hitangian, Cinemirian and Pliensbachian sitting in this very small scale synclinal structure in the half-graben. So we had reason to believe from spectral analysis that was done of the old Pries 1, the old oil and gas exploration well, that there was a Milankovitch signal in the Jurassic and probably in the upper Triassic of the borehole. So this was an early analysis, spectral analysis done by my PhD student, Alex Hudson, who took the gamma ray and did a fairly crude but effective look at the regular cyclicity. And we see some clear spike at about 25 meters, a clutch of peaks. If one proposes that's the long eccentricity, then these peaks would be around short eccentricity, some obliquity and some smeared out precession. And going on that basis, we came up with an age for the Hitangian, at least in the Pries 1 well, that was pretty similar to what Dennis Kent and others had got from the Hartford basin as well, with sedimentation rates at Pries looking pretty closely comparable to those determined from Mokris. So that was really one of the important bases for drilling at Pries. We also did quite a bit of work on the maturity and depositional, the burial history of the rocks at Pries, and I won't go into detail here with an eye on the time, but if you just look at panel C, these are Tmax values, so this is an indication of how much previous heating the organic matter has seen at that particular location. And this brown is from Mokris, green is from Pries, and purple is from a nearby location called Wilksley. And we can see that they're all pretty similar to each other, still immature as far as oil and gas generation are concerned. And that's important because in terms of organic paleo-environmental information, it should still be there in many of the molecules we recover in the Pries core. So there is a reconstruction of the history, of the thermal history of those rocks at Pries through time, reaching their maximum at the end of the Cretaceous before subsequent uplift during tertiary inversion. We also knew from some other shallow boreholes in the Cheshire Basin that there was a very good fossil record. So this is a core from a place called Wilksley, beautiful ammonites of biostratigraphic value. And we also knew from some paleomag experiments that we would get an excellent paleomag record out of the sediments of this basin as well. These are very nice for those of you familiar with paleomag records. These are really quite nice, clean, reversed and normal signals from this old legacy core material, giving us confidence for Pries. So we drilled Pries 2 as close as we practically could to Pries 1 in this location. It's much shallower than Pries 1, so I've sort of laid out Pries 1 hole on the Google Earth map here to show you the scale. Pries 2 shown for scale there. And we set up the site ready to go in October. This is what the site setup looks like, and it is actually quite a big job. I was quite surprised the scale of the site preparation that was needed and the cost of that site preparation in terms of environmental protection and best environmental practice, which was very important for us to pursue in the context of a scientific drilling program. So we set up the site, and there was some initial work setting a steel pipe through the quaternary, which is about 20 meters thick at this location to stop the sand collapsing into the hole. That was done in September. And then in October, the rig was mobilized. This is the rig in the background here, with some public outreach. Despite the pandemic, it was really important to keep the public on board. I don't know about other countries, but in the UK, there's a lot of suspicion as soon as there is a drill rig on a site that it's oil and gas related and fracking. These are some pictures of the coring in operation. So we had a blowout preventer, which was necessary to fit to the rig in this potential oil and gas exploration basin. There are here 6 meter length drill pipes, which are being put in place at the drill rig. Extraction of the core here out of the core barrel in plastic liners, which are then taken beneath this little tent here and cut. So here's a cutting of the core, 6 meter core into 1 meter sections. Those 1 meter sections are then given a basic characterization. Again, because of the pandemic, it was limited what we could actually do on the drill site. There is a Twitter account for Jet Prees, and there are some little videos as well on there of activities. For those of you who are interested, this is about the Triassic-Jurassic boundary, and this is a kind of famous disturbed horizon that we get within the Penarth group at about the Triassic-Jurassic boundary. That disturbance, the seismicity, being one of the mysteries of that particular event. So the core recovery was very good. So basically I've laid here in this diagram, we've basically got a kind of bar chart of lengths of core recovered in each 6 meter length, with core gain, in other words, too much recovery shown in blue, a dark blue, and core loss in red. So after the first few cores 1 to 7, which are on the left of the diagram, which were short and incompletely recovered in some cases, after that, core recovery was pretty much 100%. So I'm quite confident that, unlike oceanic IODP sediments, where often Milankovitch coring is done offset, that in this case, in Prees, we're not missing anything between the core runs. We seem to have captured pretty much every centimetre through most of what we drilled. So that's the 100% line along the top in the bottom diagram. These are just short cores for operational reasons. They're still 100% recovery. The lithologies.
Just a small question.
Yeah.
What does it mean, core gain? Core gain,
it means that you drilled, say you drilled 6 meters, but you picked up 6 meters and 10 centimeters of rock. In other words, you recovered more than you drilled.
Yeah, but on the next one, it will not. It will be missing.
Well, that's exactly the point. So if on the first core you recover everything except the last 10 centimeters, the next core you might recover the 10 centimeters that you didn't get the first time. And so you've always kind of got this balance between not quite 100% recovery and just over 100% recovery.
Okay.
So the lithologies, exactly what we were hoping for, dark, generally dark grey mudstones. I think these are zoophycos here. Correct me if I'm wrong, if you recognise those differently. Those, I think, are indicative of relatively deep water. We get them in Mokros, but we don't get them at the outcrop elsewhere in the UK Jurassic. So maybe below a storm wave base for much of the rock. And this whole meter length core you can see here going from dark to light We saw this typically all the way through the Sinemurian and the Pliensbachian and the Hitangian, and it looks very much like the Mokros record of precession cyclicity. Not everything went according to plan, so if we plotted depth of the borehole versus number of days, which is shown here, and the blue line was what we planned, and the red line shows the actual, you can see that quite a lot of things went wrong. So particularly at this stage here, which was where the blowout preventer was fitted, that took much longer than expected. Then we made good progress, and then we had major mechanical failure of the rig for 10 days in the middle here. And then we started again, and at this point we ran out of money, basically. And so it was always the case that we knew we wouldn't necessarily get to 850. It was important that we got to 600 meters because that's the base of the Jurassic, and indeed we did get beyond the base of the Jurassic, so that's crucial. We had some mishaps like melted liner because of pump failure where the mud was not circulated properly, and that gave us poor recovery for one little bit here in the Triassic. By and large, the fossils recovered were excellent. So you can see this beautiful ammonite that is mimicking our logo for the JET project. This is an ammonite indicative of a particular zone in the lower Pliensbachian. We had ammonites all the way through, very common, but also these thick-shelled fossils that are very good for the chemical, for chemostratigraphy and for paleoenvironmental proxies. Despite the pandemic, we made a lot of progress doing some initial sampling. This is PhD student Mengzhe Zhang and Clemens Ullmann over here in the background in the BGS core scanning facility, where sampling has been going on for magnetostratigraphy, for isotopes, for ammonites, for nanofossils. But the core scanning, we have a whole range of geochemical and geophysical measurements, including gamma, density, magnetic susceptibility, radiography, and elemental abundances. So that's all in progress. This was some early data just to practice on Mokros, showing you the kind of cyclicity that we are picking up from PREs as well, but I can't actually show you the data yet because it's not, the quality control has not been done on those data sets at this time, but it looks very promising. And so basically we have here at a low resolution natural gamma ray from the core scanning versus the natural gamma ray from the downhole logs, which will allow extremely precise and accurate core log integration. All the material will be stored at the BGS, at the repository, the Geological Survey. There is a 2-year moratorium on access to materials, but it will be publicly available like any other material at the BGS after that. And there will be some limited CT scanning of the cores available as well. So second last slide here is just to summarize very basically what we recovered. Everything from the Quaternary, the entire lower Jurassic going from Pliensbachian through Sinemurian as predicted, through Hitangian, all marine, into the upper Triassic, and these complicated beds at the boundary were well recovered. I show no detail on the lithological log here, but you can see from the downhole gamma ray that there is a lot of lithological detail there still to come out. The ammonite evidence is really good, and in fact we even have, I've put one ammonite on here because it was so important. Biferiferous Donovani is the marker for the base of Pliensbachian, so we very precisely define the stage boundary in the core.
Steve, you're muted. You're muted.
Yes, Steve, you need to, yes.
I'm back. I'm back and I'm finished. So I'm not sure whether you missed my conclusions or not.
Maybe you should put back your last slide, so we to be sure that we didn't miss anything.
Okay. This one?
No, we were at the previous one.
Okay. So, well, this is just a statement in words. Excellent core recovery. It looks very promising for all the methods we want to apply: magstrat, biostrat, chemostrat, and astrochronology. There's a fantastic downhole logging data set, and I think there will be a fantastic fantastic data set from the scanned core as well, using this new BGS core scanning facility. So there's much work to do. The team is now 70 scientists big, the JET team, and like I say, it's a snowball that's getting bigger and bigger, and I can see that we've got enough data now and materials to keep us going for the next 10 years. Thank you.
Thanks a lot, Steve. I clap on my own, but thanks a lot, and thanks for sharing this very nice work very freshly. And so we have, there is some, I didn't notice there was some clap possibility on the Zoom. So now we are open for questions. So please raise the small hand to give you the and when you speak, please of course unmute your microphone, but as well your camera. Yes, Felix.
Well, thank you, Steve. An outstanding lecture. I greatly enjoyed it. I have an innocent question. I came recently across a criticism of the Middle Jurassic timescale in DTS 2020, saying that with the duration of the stages that we published, or you published, the sedimentation rates were entirely unreasonable, showing that the stages are too short. Now, this is something that is an ongoing research and will take many years to resolve because we don't have such a good cyclic record. But what I'm curious about is the fact that they pointed, the author pointed at a database that exists for environments where you get unreasonable high or unreasonable low sedimentation rates. And your type of study with so many cyclic sections seems to be an outstanding example where you could do such a thing. That's my question. Right.
No, that's very interesting. And I haven't seen that criticism, so I'd be interested if you could point me very specifically to it. The Middle Jurassic is, I mean, just a slight aside, the Middle Jurassic is, it's kind of poor cousin in the Jurassic at the moment. It does tend to get squeezed by extension of the stage lengths in the Upper Jurassic and the extension of the stage lengths in the in the Lower Jurassic. So I think there is a kind of major scientific issue to address there. Yeah. So in terms, well, can we illustrate a range of sedimentation rates in similar environments in the Lower Jurassic? For sure, yes, absolutely. Sorry, Felix, in terms the specific question that I can address with respect to the Lower Jurassic, do you want to just come at it again so I understand it?
No, it's just a very innocent comment, basically, that Pete Sadler, in this particular case, that's a database that author that is publishing. It's in prep papers, not published.
Okay.
Refers to the Sadler database that shows sedimentation rates for a large number of environments, and shows that stages like Middle Jurassic stages have sedimentation rates that are entirely unreasonable for the duration of the stage, which means the stage is too short. And now that's a different scientific problem, but in your case, since you have such fantastic, you have so many sections, cyclic sections that you can correlate with slightly different in environment, you could kind of improve upon a database for the lower Jurassic in terms of sedimentation rates of specific environments.
Yes, yes, okay, right, yes, okay, I understand that. Yes, that's interesting, and we could certainly, that would be quite an interesting test to do, particularly, I suppose, coming at carbonate platforms, which might be might be what he's getting at.
Exactly. Well, thank you very much.
Yeah.
Yes.
Paul?
Hi, Steve.
Hi.
Did you find something lithologically similar to the paper shales at the base of the Lias?
Yes, very much so. Yes. So the base of the Hitangian is apparently organic rich laminated mudstone.
Does it have a really abrupt contact with something like the mollusk-bearing white lias, old term white lias, the upper Langport?
It has an abrupt contact with a more siliciclastic rich unit, which is kind of pinstripe, very fine sand and siltstone, like the cotton beds.
Okay.
There are no mud cracks like you get at the Triassic-Jurassic boundary further south, but then of course in a core you might easily miss the giant mud cracks, but you certainly do get the seismite and the deformed beds are very much there.
Are there red beds in the at the top of the lower coffin?
There are red beds within the cotton member, not at the well, are they at the top of the lower cotton or not? I don't know, but they are certainly red beds within the cotton, absolutely.
I had a question. What is the data policy? What is for a project like that? What is the you mentioned it a little bit, but I didn't really understood. The core is stored in this repository.
Yes.
And what is accessible to people? When is the data public? When is it public, or what is the general policy?
So unpublished data are under a moratorium for two years. The data will be published before that 2-year period. There's no doubt, particularly the sort of basic downhole log data, and some of the kind of key parameters like carbon. There will be a carbon isotope record, I'm sure, published very on. So those data and the generated data will be published before 2 years. After 2 years, the moratorium is lifted. In terms of that, will mean that anybody can get access to samples. I'm not actually, even though I am the PI, I have to admit, I'm not actually sure about other data that are generated, such as the downhole data. At what point, if it's not published by them, at what point it will be made available. I think the rules are a little grey as far as that is concerned.
Mm. But there is no general policy that is made for who is the funder here, the main funding agency?
Well, I mean, I think therein is lies the difficulty, is that there are multiple funders who will have slightly different policies. So the major funder for the drilling operations is the ICDP, International Continental Drilling Program, and they generally take their lead from NSF in terms of those sorts of policies. for our project, we also have a very large amount of funding from NERC. There isn't a kind of legislation in terms of precisely moratorium periods and so on, but generally NERC will expect there to be as much public access and scientific community access as possible. And then there are a number of other funders that we have as well on a much smaller scale.
Okay, thanks.
So, Shaq, there's always a kind of balance here to protect the interests, really, of those people who've spent many years of their life,
of course,
of producing the data, but also making it as widely available to the scientific community as possible to get as much scientific impact as we possibly can. So it's trying to balance those two things.
Yes, I know this problematic, and but I've seen what they are doing now in space science. It's the second part that takes over, and the moratory period is very short, even for people who invest 10 years in the in the project, and they have to make a lot of science quickly before the data is released. But of course, the people who know well the data are always one step ahead, and it's sometimes collaboration is better than competition.
Yeah,
but the general idea is to make for the funding agency who make a big space mission, who can take 20 years to set up. The idea is to make the most possible science out of the data.
Yeah. And as far as JET is concerned, then definitely collaboration is the name of the game.
Any other question?
Oh, I have another one.
Yes, sure.
I couldn't help but notice what was pretty apparent cyclicity in the log, a pretty large scale. I'm sure one of you guys in your team has already subjected that to some initial Fourier analysis. I couldn't resist. I would have done it 30 seconds after it arrived on my desk. Do you have any general sense of what of how that matches MOCRIS, and especially interested in the 400K cyclicity?
Well, the short answer is no, actually, because the data really are so fresh. I mean, I only plotted the data against that diagram yesterday afternoon. So no, actually, even though...
So what's the problem, Steve?
The rest of the time was spent practicing this talk. But as you know, yes, we do have a number of site-based stratigraphers who will be like you, will be really keen to get to grips with the cyclicity in all those different data sets. And I think one of the things actually that's quite interesting about this data set is that there will be a whole range of parameters that we haven't looked at before, particularly because we've got so much. We'll have so much XRF data as well as all the geophysical data. So there's going to be thousands of different paleo-environmentally significant parameters that we could look at in terms of the cyclicity. There's a real resource there to mine over the years. And so we can get away from looking just at carbonate, for example, which we had to do before, which was obviously multifactorial. It was partly diagenetic, partly in terms of productivity. And we can start to look at things that really, do actually just mean grain size, or rather silt clay ratio, or whatever it is.
Yes, Jean-Baptiste?
This is not a question, but by now I'm working with Mathieu Martinez on my PhD, and I'm working on the upper Triassic series of Paris Basin. And I wanted to know if your data about Trias in England were workable, or just to know, to make comparisons.
So that's interesting. That's the one thing I think we did not manage to do. We basically ran out of money before we got much of the way through the Mercia mudstone, which is the uppermost Triassic. But we did get about 40 meters, 50 meters of these Playa Lake type red, green, black late Triassic mudstone deposits, and they do look very cyclic. So I think there absolutely is there's mileage in looking at that upper Triassic sequence. So we get, for example, beautiful cycles of red mudstone interbedded with what look like laminated dolomite, microbial dolomite deposits, which presumably represent some kind of ephemeral lacustrine shoreline, and then complete evaporation as well. So the climate cycles beautifully expressed, I think, in those upper Triassic mudstones.
Yeah. Okay. Thank you.
What we did find in the upper Triassic was a lot of fractures. That was actually one of the technical problems. And those fractures might very well relate to the salt tectonics that I alluded to in terms of the origin of that basin. So I think the upper Triassic stuff was rafted on late Triassic salt that was flowing away, producing the subsidence for the Jurassic.
Yeah. Okay. Because we have I think we have the same lamination in the Paris Basin, so it will be interesting to compare it. Yeah, in a few ways.
Yeah, good.
Paul?
In the blue anchor that I've seen along the Somerset coast, there's often evaporites in it. Did you see anything like that in the Trias?
We didn't get that far down. There are known to be evaporites. In fact, they're commercially exploited eventually in the Trias. There's quite a thick evaporite deposit. Well, there are two. One of them, called the Wilksley halite, is about 150 meters thick at that location, and then there's another one that's about 200 meters thick just below it.
Well, I meant at the top.
No, at the top we didn't see anything that looked.
No gypsum.
Not in what we cored, but the Pries 1 cuttings have reported gypsum from the same interval.
What was the total cost of the drilling?
About, in terms of dollars, probably about just over $2 million.
Okay.
It's expensive. There's no doubt about it that it's expensive, and I mean, it's interesting that a lot of the money that you spend on these drilling projects is not the actual coring. It's all the preparation that you have to do beforehand. So getting the permissions, getting all the environmental stuff done, constructing the site correctly, getting drilling supervision in, all these things, it adds £100,000 here, £100,000 there, and eventually, even though the cost per meter of core once you're actually there is relatively small, all these background sunk costs are very large.
Okay, but 2 million is still reasonable. It's not. It's something you can you can manage to get. it's not like a small space mission of $200 million, which is much more difficult. It's not the same level.
Yes,
but still.
Yeah, it's a lot of money. But I would encourage. I mean, I really would encourage people to think about, you know, what next. I think, you know, I'm not going to put in another proposal at this stage, but there's a lot of mileage in generating new proposals and keeping ICDP busy with new proposals that build on this in the future.
But do you think that having only one core is a major problem, or?
No, particularly because there is such value in these in the legacy cores. I mean, I only mentioned Mokris, but there are other boreholes as well, legacy boreholes, which are fantastically underexploited, that are just sitting there in the archives. And it may be true in other countries as well. I just know this to be the case for the UK, for the Jurassic. I mean, so if you kind of widen that out, there must be huge resources across Europe and America that are just not, that are sitting there and haven't been used.
So you think the missing part of the core can be retrieved in the other record? Is that what you mean?
Well, not the missing part, but the Pliensbachen and Taurasian is very well represented in other records, absolutely. So that we get the whole Lower Jurassic by a combination of two plus some other boreholes.
Any other question about this core, about the JET project? So I don't see.
Yeah, I do again. Sorry.
Yes, sure.
Is there something citable we can use about the completion of priests? Like, for example, for an ICDP proposal due Friday.
Oh, yes. Well, it's on the ICDP website.
Okay, I guess they know about it.
Yes, if you could cite the highlights, because it says on the website, the coring is complete.
I'll do that. And this is your first presentation you've done?
It is,
You've done one? Okay,
no,
so I'll be able to maybe cite the recording as well, perhaps. Is that okay, Jacques?
Yeah, of course. By the way, yes, the talk is recorded, and I've put online the talk of Felix. You've seen that. That was took a little bit of work, but then now it is. It will be shorter, and it should be available. So there is an AstroGeo YouTube channel, which you very easy to find, and I'm glad that I think the quality is good. So I think it would be a very something very easy to refer to. That. Any other question? Other question? There was a...
There is a hand up.
Yes. Who was the hand up?
Fatima Zara.
It's me.
Yeah.
Hello, Steve.
Hello.
I have a question about the project, the Early Jurassic Earth System and Timescale projects. The question is how many sections you are going to study during this project?
Well, mostly the two that I've talked about, Mokris and Pries in particular, but there are some outcrop sections that are also rather important. So the ones associated with the GSSPs in Robin Hood's Bay and in Somerset, there's still some important correlation to be done from the outcrop into the core sections. And we've done quite a lot of work on that already, but there's more to do. So those are the main ones that are still part of JET.
So thanks again, Steve. You made a very, very nice work despite your very busy schedule, and you made a very clear talk. So thanks. I think thanks for everyone to be here as well, and we'll meet again in 1 month, and I will put relatively fast the record on the website.